Hello, in this video we are going to discuss about electrostatic potential in the university levels physics. Now from vector analysis we know that the curl of a vector, if that is equal to 0, then that vector must be the gradient of a scalar quantity. In this case, if we are treating the case, if we are using the case on the electric field, well, the curl of the electric field also is equal to 0, and therefore we can say that the electric field is going to be the gradient of a scalar quantity. We put a negative sign over here uh, on that gradient of this scalar being equal to phi over here. So this negative sign, we'll discuss about how it really came up over there. This is basically out of convenience. Now the curl of the electric field vanishes, as we can see over here. Now in this case we are observing that taking the curl of the term, and that term which we have taken the curl of, that exists in the expression for the electric field. So the charges are obviously the constant terms. They do not vary because of the charge invariance over that given space. But with that parameter that we have taken the curl of, that vanishes. If you wish to know how, then we can use the vector identity. Let us have that. We'll be using a case where if we put r minus the r naught to be equal to some other vector a, and we put 1 over r minus the r naught and the cube of it to be equal to some scalar quantity. Let us take that as in this case be chi. So what we get is, we take the gradient or the curl, in this case curl of chi a, chi being the scalar, and that is simply equal to the gradient of the scalar times gradient of the scalar taken curl with a, and then that is followed by adding the scalar quantity multiplied to the curl of the vector. Now here the vector term is going to be the numerator, and the denominator, as we have put it, is the scalar. So if we write this in that form above, so what we get is that the curl of this entire thing, that is r minus the r naught divided by the modulus of r minus r naught whole cube, is going to be equal to the gradient of 1 over r minus r naught modulus cube cross product with r minus r naught, the vector, plus the second term carrying 1 over r minus r naught cube, and then we have the curl of the vector r minus r naught, just the expression that we gave over here. Now this curl that we are speaking of, that is actually the differentiation of that given quantity, whatever we are taking the curl of, the differentiation of that term over a varying position vector. That is, the curl is simply, if you have this operator that we are talking about, that is the gradient operator, and that is simply d over dr, but that's a variable r that we are talking about when we are taking the curl. So in that case what we get is, for the second term, obviously it's going to end up with an r, so this is going to go to 0. And as for the first term, that's the gradient of that scalar is going to result in minus 3 over r minus r naught mod raised to the power 5 r minus r naught, and that again is as you can see, is having a cross product with r minus r naught. So the cross product of the same terms that is also going to go to 0. So eventually what you find is that the curl of E will be 0 as we had predicted earlier. And with the curl of E being equal to 0, the E or the electric field must be the gradient of some scalar quantity. In this case, we are taking the negative gradient of the scalar quantity, that is phi, and phi here is what we take as the electrostatic potential. That varies over the R as E varies over R. Although the variation is not the same as that of the electric field varies as inverse square of the distance from the given charge distribution or from a single point charge. In case of potential, of course, we are going to observe that it varies just inversely as the distance. Now, what we also get from this expression is that if we are to consider obtaining the case of obtaining the value of the potential, then we may just integrate this electric field over a given range extending from a reference point. Let's take that as since we have already used R naught, we are taking R ref as the reference point, and then we are taking a final point as R, and the negative sign goes shifts to the other side. So what we get is, or we take the negative of all of that. So what we get is the negatives cancel out when we give the value of the electric field in terms of the scalar, and what we get is this R from the reference to the final R, and the negative have vanished, so gradient of that potential R dot product with dr, and that is going to be equal to, eventually that's going to result in phi r minus the phi at the reference point. Now, because we usually consider the case of a very large distance taken from a given charge distribution to have no such impact, or to have no such to not get affected by the electric field of the distant charge. So we can say that if we refer to the point or take the reference point to infinity, then there the electric field and also the potential, they will not exist. So finally what we can write is phi r is equal to the electric field taken over the distance dr extending from infinity to any given point in consideration. So that is the definition of the potential at a particular point when we take the reference point as infinity. Now, the potential is simply going to give us the work that is being done in order to bring the charge from infinity to the point in consideration per unit charge, because if we are multiplying a charge over there, then we are going to obtain the work, because charge multiplied with the electric field is the force, electrostatic force, and that with the distance is going to give us the energy invested, or the potential energy that is stored in the system. Now that potential energy stored in the system per unit charge is how we define the potential. We have been defining that in the previous cases in the junior level physics, and that is exactly what we have done, just in a different approach, considering the vector analysis and the case of the curl of the electric field going to 0. The curl of the electric field going to 0 is always going to tell us that the electric field here is irrotational. The fields which are irrotational, they have their curl to be equal to 0, and that is the case with the electric field as well. Then if we are to consider the potential difference between any two positions, then we will simply take the limits from the first point to the second point, or with the minus sign we'll take it the other way around. Now in case these 2 points, they lie at the same position, that means the charge or the potential difference is taken over an entire cyclic path, then that is eventually going to give us a zero. And what that means is that the curl of E, what that means is that the electrostatic force that we are considering over in this case, with the work done being zero, the electrostatic force results in a conservative force. And that is exactly what I have written over there, that the charge is brought back to its initial position over a closed path, then the resultant or the potential difference becomes zero, and hence the resultant work done is also zero. Then we have the electrostatic force to be a conservative one. Now the units of the electric potential in case of the SI system or the MK system that we have, in SI units we have that as joule per coulomb, that is the work done per unit charge, and that is also called as the volts. And the dimension is obviously going to be joule per coulomb, means joule is ml2t minus 2, and coulomb is simply a times of t, so that is eventually going to give us t raised to the power minus 1 times of a, which is the case of the dimension of the, well, it is per unit charge. Per unit charge means it's going to be in the denominator, my bad. It'll be actually minus 3 instead of minus 1 for the case of the time, the dimension of time over there. So that will be minus 3 and this will be minus 1. Better. Now with the electric field being the negative gradient of potential, for the potential being constant or same over a given surface, which we call as the equipotential surface, for the potential being constant, we'll have the electric field to be normal to that given surface from the geometry of it, from the mathematics of it. So with the gradient will obviously lead to zero, and that is why we'll have the electric field to be normal to that surface, and which has been represented in the figure below. Now these concentric circles that you see, they are actually in three-dimensional case, they are concentric spheres, and those lines emanating or moving outward radially represent the direction of the electric field in relation to those equipotential surfaces. Remember, the radius is always going to be perpendicular to the tangent drawn to the surface, and so the electric field will always be directed normal to a given equipotential surface. Those concentric spheres will be equal in potential as their distances from with respect to the charge that is placed at the center is always going to be the same, and with the same distance we'll have the same potential on each of those spheres. Obviously the potential difference will be there between the concentric spheres, but for a given sphere with a fixed radius, the electric potential is going to be constant. Now with the expression for electric field and with the expression for the case of phi, that is the potential that we have written right at the top, what we can obtain is that we'll be using the expression for potential to obtain the value of phi. So phi r at any given position is going to be the negative of q over 4 pi epsilon naught, which is how we express the electric field dr lies as such and divided by r squared because the electric field varies inversely as the square of the distance. So we end up with q over 4 pi epsilon naught times of r as predicted or as mentioned earlier, that the potential is just going to be inversely proportional to the distance, as opposed to the case of the square of the distance in case of the electric field. That's the basic difference between the potential and the field with respect to the variation in terms of distance. Now, from the standpoint of electrostatic behavior, the materials can be divided into classes, two basic classes, that are the conductors and the insulators. Now, the conductors are the ones which have free charge carriers. Mainly, the the solids are the ones that are considered for conduction, like wires and cables, but they have the charge carriers in the form of electrons. But there are also liquid materials which have the positive charges to be flowing, positive ions, and they are free to move throughout the material, those charge carriers, and it is they who uh, conduct the electrical current that is flowing across the uh, conductor when the conductor is subjected to an external electric field. Now, and the current continues to conduct throughout the conductor as long as the field exists, and metals are obviously good conductors. But in case of dielectrics, they have charged particles but they are not free, but they are bound to the molecules. And as a result of that, when an external field is applied, the charged particles, well, they may be slightly shifted in position, but they remain bound to the molecules. Most of the non-metallic solids, they are insulators. And there lies a category between that of the conductors and the insulators, and that is the semiconductor. The semiconductors have the properties which lie between that of the conductors and the insulators. In static electric fields, these materials behave like conductors, but their transient response is slower. Various materials at low temperatures offer no resistance to the movement of charge, and they are called as superconductors. So we have that as well. Now, it is important to observe some of the properties associated with the conductors before we move ahead further into the topic. Now, the first of the properties states that in case of a charged conductor, under static condition, the potential must be the same at all points. That is, in static condition, the conductor is an equipotential region of space. Suppose we had a potential difference, that is del phi was finite, then we must have the electric field to exist. And with the existence of the electric field, there will be a flow of current, and the electrostatic condition is not maintained. So under static condition, electric field is zero, and so the potential is going to be the same. That is, we are going to have an equipotential region, and that is for the case of a conductor. Secondly, the net charge of a charged conductor will always reside on its outer surface under the static conditions. Now, because the electric field, as we have seen in the first property, that it vanishes, we'll also have the divergence of the electric field to vanish, that is equal to 0, with E being equal to 0. But the divergence of the electric field is simply the charge density over epsilon naught. So that simply tells us that the charge density is going to be 0. And because the charge must exist, so the only place left for the charge to reside on the is on the surface of the conductor. Now, also under static condition, the electric field just outside a charged conductor is perpendicular to the surface of the conductor. Now, had that not been the case, had it been at some angle with respect to the surface, then there would exist a tangential component which will cause the motion of charge along the surface due to the field acting on it, and that would create a non-static condition. So the static condition is lost in that case as well. So let's just visualize this. Now here's the surface that we are considering, a portion of that surface, and let us say that the electric field is making a certain angle over here with respect to this surface, with respect to the tangent to the surface. So let's have that angle as theta, or probably phi. Since we are using phi as potential, we'll take it as some other value. So we'll keep it to theta. There is a certain angle, so that is theta over here. Now, with this being the direction of the electric field will also have a component which is acting tangentially as mentioned, and that tangential component, with the charge residing on the surface, it will act on those charge, and electric field acting on a charge will apply force on it, and the charge tends to move. But that won't be possible, or that won't really help the static condition. The conditions will no longer be static. So under static condition, the electric field always has to be perpendicular such that its tangential component is going to be equal to 0. So if the electric field is along this direction, not this direction, then cosine component is going to end up as 0. Because as you can see now, the value is 90 degrees for that theta. It is at right angles, and cosine 90 is always going to be 0. Now the magnitude of the electric field just outside the charged conductor is going to be sigma over epsilon naught, sigma being the surface charge density. Here we had written rho is the volume charge density, and sigma is the surface charge density. Lambda usually is considered as the linear charge density. Now if we are considering a surface of the conductor, and we'll consider a very small box which is the imaginary Gaussian surface. The surface below has the direction over in this direction, and the surface above has the direction outward, and so will be the direction of the electric field along that direction, because the electric field cannot remain inside the conductor. So this direction, although the surface is in this direction, but the electric field over here is going to be 0, and the tangential electric field does not exist. So along that curved cylindrical portion, we won't have any flux linked to it. Now from Gauss' law, we have the net flux that is associated with a closed surface, that is given by E. Let us say that top surface has the surface area ds, and the charge that is being that would be contained in that top surface is sigma times of ds. So the total charge that is contained in within that surface is sigma ds over epsilon naught as per Gauss's law, and then we have the ds cancelling out. So we have the magnitude of the electric field. Obviously the electric field is directed outward, normal to the surface, as we have discussed earlier. So that will be sigma over epsilon naught, and if we are considering the normal unit vector to be equal to as n cap, then we'll have E to be equal to sigma over epsilon naught n hat in that direction. Now, as the fifth property, we'll be determining the force per unit area on that surface of the conductor in static condition. Now, we know that there is an electric field that is associated with a certain area, but is there any force associated? Because obviously there will be some charge and there's an electric field that is acting. but that electric field is due to the charge that is present on the surface. So the charge does not apply a force on itself. Its field is directed outward as we see there. But is there a force existing on that area? We'll check that out. So if we are considering that same figure, we'll just consider another case where we are taking a point a bit further up. The point was closer, so the box that I had considered, the cylindrical box that we had considered, that was a small one. Now we are extending it a bit further. Now what happens over there is that we still have the box which is very close to the surface. So we have that cylindrical box coming up once again. Now we tell that the electric field due to this box at that point is going to be E1. But the total electric field that will be linked, or that will be observed at that point, that will be equal to the electric field due to that small portion which has the area ds that we said over here or over here. Then that plus the electric field that is existing because of the rest of the surface that is available. So this rest of the surface that is available, the field due to that portion, or probably even greater portion that I haven't really shown in the figure, the rest of all of that portion is having an electric field E2 at that point. Now in order to determine that electric field, what we'll do is we'll name this point as P, and we'll have another point, let us take that as P prime over here within. So just like a mirror case, if we are having a P up, we are having a P prime within the conductor. Now the P prime will also experience the same thing. There will be the electric field, but the electric field E1 now considered for that small box that we'll have, that will be acting in the downward direction. Now with the electric field acting in the downward direction, considering the reference point, we'll have electric field to be minus E1 at this point, because we are taking E1 in the positive sense. And the rest of the electric field E2 will be added to it, and then finally the net electric field, as we know, inside is going to be 0. So what we get over here is that E1 is simply equal to E2, and so the net field that we'll be getting, or E2 that we'll be getting from the net field. Now what will be the net field over here? Well, the net field is going to be obviously equal to the same, because even if the point is further up, the electric field that will be along that direction, because in this expression that you see there is no distance involved, so the electric field is going to be the same along that line, and we are maintaining that line above that box that we have drawn. So E there has the magnitude of sigma over epsilon naught, and E1 and E2, as we found over here to be equal from this equation, that is minus E1 plus E2, well, we are taking the modulus over here, so we are actually not the modulus over there, my mistake, we are taking the modulus over here. This is pretty unclear, let me just write it for you, and I remove the modulus over there from where I have drawn that. So I remove the moduli over there. So in that case, the E1 plus E2 is going to be equal to 0, and that is going to result in E1 being equal to E2 in terms of magnitude. And then we'll have 2E2 or 2E1 to be equal to sigma over epsilon naught. We'll keep the E2 over there instead of E1. So E2 is simply sigma over 2 epsilon naught. Now with E2 being equal to sigma over 2 epsilon naught, that is the field due to the rest of the surface which will be acting on that small portion ds. So the force that is experienced by that small portion ds is going to be the charge that is contained in that. Now the charge that is contained in that is simply sigma times of ds, and the field due to the rest of the portion that we have is E2, which we have obtained to be equal to sigma over 2 epsilon naught. So that gives us the value of the force to be equal to sigma squared over 2 epsilon naught times of ds. Now sigma, I'll take it to the other page because we are having some issues with the space over there. So taking it over to the other page, I hope you remember the notations that we have used previously. We'll refer to that just by going back. So we had left with sigma squared over 2 epsilon naught, which is not clearly visible, times of ds being the force over there on that small area. So we have force to be equal to sigma squared over 2 epsilon naught times of ds. Now the force per unit area is obviously going to be sigma squared over 2 epsilon naught. Sigma squared over 2 epsilon naught being the force per unit area, we can, as we know that sigma over epsilon naught is simply E, so we keep one of those sigmas over here, we keep the half over here, and sigma by epsilon naught is going to be E. So this is half times of sigma E, or we can also write it as half of epsilon naught times of E squared, with one epsilon multiplied at the top and another multiplied in the denominator. In this term we'll get epsilon naught squared. Sigma squared over epsilon naught squared is E squared, and an epsilon naught multiplied in the numerator term. So half of epsilon naught times of E squared. So as the surface is equipotential, the direction of this force per unit area will always be directed normal to the surface, the unit being Newton over meter squared. What we also get from this property is that with the force considered over unit area, the conducting surface, let me write that for you as I have been doing, the conducting surface being equipotential, the electric field as well as the, or we can say the magnitude of the electric field as well, the electric field as well as the surface charge density, they are greater on the parts of the surface of the electrified conductor which are strongly curved, because with those curved strongly, suppose we are considering a pointed surface of a conductor. Now in that pointed surface obviously the value of ds is very small, as it is ds is small, so we are considering ds to be very small, and the smaller the value, the force per unit area is going to be very less, and so this value, or this expression that we have over here, that is going to be much higher or greater in magnitude with the decrease in the denominator term. And that is why the electric field that is associated in that at that point is going to be much greater, and so will be the case with the surface charge density associated with that point. So that will be all from this video on the discussion of electromagnetism. Here we are discussing the initial portions on electrostatics. We'll be discussing more on this topic, at least in the next video. I can say that we'll be discussing about the electric dipoles, although we have obtained the general expression for the dipoles in the preliminary level, in the school level, that is 11th and 12th standard, but we'll be obtaining a much more efficient one which will be helpful to discuss about charge distributions and the multipole expansions as well. So that's it from this video. Till next time, thank you for watching.